Enriched uranium is a type of uranium in which the percent composition of uranium-235 has been increased through the process of isotope separation. Natural uranium is 99.284% 238U isotope, with 235U only constituting about 0.711% of its weight. 235U is the only nuclide existing in nature that is fissile with thermal neutrons. Enriched uranium is a critical component for both civil nuclear power generation and military nuclear weapons. The International Atomic Energy Agency attempts to monitor and control enriched uranium supplies and processes in its efforts to ensure nuclear power generation safety and curb nuclear weapons proliferation. During the Manhattan Project, enriched uranium was given the codename Ore Alloy, a shortened version of Oak Ridge Alloy, after the location of the plants where the uranium was enriched. The term ore alloy is still occasionally used to refer to enriched uranium. There are about 2,000 tons of highly enriched uranium in the world, produced mostly for nuclear weapons, naval propulsion, and smaller quantities for research reactors. The 238U remaining after enrichment is known as depleted uranium and is considerably less radioactive than even natural uranium, though still very dense and extremely hazardous in granulated form. Such granules are a natural byproduct of the shearing action that makes it useful for armor-penetrating weapons and radiation shielding. At present, 95% of the world's stocks of depleted uranium remain in secure storage. Grades. Uranium, as it is taken directly from the Earth, is not suitable as fuel for most nuclear reactors and requires additional processes to make it usable. Uranium is mined either underground or in an open pit depending on the depth in which it is found. After the uranium ore is mined, it must go through a milling process to extract the uranium from the ore. This is accomplished by a combination of chemical processes, with the end product being concentrated uranium oxide, which is known as yellow cake. Contains roughly 60% uranium, whereas the ore typically contains less than 1% uranium and as little as 0.1% uranium. After the milling process is complete, the uranium must next undergo a process of conversion to either uranium dioxide, which can be used as the fuel for those types of reactors that do not require enriched uranium, or into uranium hexafluoride, which can be enriched to produce fuel for the majority of types of reactors. Naturally occurring uranium is made of a mixture of U-235 and U-238. The U-235 is fissile, meaning it is easily split with neutrons, while the remainder is U-238. But in nature, more than 99% of the extracted ore is U-238. Most nuclear reactors require enriched uranium, which is uranium with higher concentrations of U-235, ranging between 3.5% and 4.5%. There are two commercial enrichment processes, gaseous diffusion and gas centrifugation. Both enrichment processes involve the use of uranium hexafluoride and produce enriched uranium oxide. Reprocessed uranium is a product of nuclear fuel cycles involving nuclear reprocessing of spent fuel. REPU recovered from light water reactor spent fuel typically contains slightly more U-235 than natural uranium, and therefore could be used to fuel reactors that customarily use natural uranium as fuel, such as CANDU reactors. It also contains the undesirable isotope uranium-236, which undergoes neutron capture, wasting neutrons and creating neptunium-237, which would be one of the more mobile and troublesome radionuclides in deep geological repository. Disposal of nuclear waste. Low-enriched uranium. Low-enriched uranium has a lower than 20% concentration of 235 U. For instance, in commercial light water reactors, the most prevalent power reactors in the world, uranium is enriched to 3 to 5% 235 U. Fresh LEU used in research reactors is usually enriched 12% to 19.75% U-235, the latter concentration being used to replace HEU fuels when converting to LEU. Highly enriched uranium. Highly enriched uranium has a 20% a higher concentration of 235 U. The fissile uranium in nuclear weapon primaries usually contains 85% or more of 235 U, known as weapons grade, though theoretically for an implosion design, a minimum of 20% could be sufficient usable, although it would require hundreds of kilograms of material and would not be practical to design. Even lower enrichment is hypothetically possible, but as the enrichment percentage decreases, the critical mass for unmoderated fast neutrons rapidly increases, with, for example, an infinite mass of 5.4% 235 U being required. For criticality experiments, enrichment of uranium to over 97% has been accomplished. The very first uranium bomb, Little Boy, dropped by the United States on Hiroshima in 1945, used 64 kilograms of 80% enriched uranium. Wrapping the weapon's fissile core in a neutron reflector can dramatically reduce the critical mass. Because the core was surrounded by a good neutron reflector at explosion, it comprised almost 2.5 critical masses. Neutron reflectors, compressing the fissile core via implosion, fusion boosting, and tamping, which slows the expansion of the fissioning core with inertia, allow nuclear weapon designs that use less than what would be one bare sphere critical mass at normal density. The presence of too much of the 238 U isotope inhibits the runaway nuclear chain reaction that is responsible for the weapon's power. The critical mass for 85% highly enriched uranium is about 50 kilograms, which at normal density would be a sphere about 17 centimeters in diameter. Later U.S. nuclear weapons usually use plutonium-239 in the primary stage, but the jacket at Tampa secondary stage, which is compressed by the primary nuclear explosion, often uses HEU with enrichment between 40% and 80%, along with the fusion fuel lithium deuteride. For the secondary of a large nuclear weapon, the higher critical mass of less enriched uranium can be an advantage, as it allows the core at explosion time to contain a larger amount of fuel. The 238 U is not fissile but still fissionable by fusion neutrons. HEU is also used in fast neutron reactors, whose cores require about 20% or more of fissile material, as well as in naval reactors, where it often contains at least 50% 235 U, but typically does not exceed 90%. The Fermi 1 commercial fast reactor prototype used HEU with 26.5% 235 U. Significant quantities of HEU are used in the production of medical isotopes, for example molybdenum-99 for technetium-99 meters generators. Enrichment methods. Isotope separation is difficult because two isotopes of the same elements have very nearly identical chemical properties, and can only be separated gradually using small mass differences. This problem is compounded provided by the fact that uranium is rarely separated in its atomic form, but instead as a compound. A cascade of identical stages produces successively higher concentrations of 235 U. Each stage passes a slightly more concentrated product to the next stage and returns a slightly less concentrated residue to the previous stage. There are currently two generic commercial methods employed internationally for enrichment: gaseous diffusion and gas centrifuge, which consumes only 2% to 2.5% as much energy as gaseous diffusion, with centrifuges being at least a factor of 20 more efficient. Some work is being done that would use nuclear resonance. However, there is no reliable evidence that any nuclear resonance processes have been scaled up to production. Diffusion techniques. Gaseous diffusion. Gaseous diffusion is a technology used to produce enriched uranium by forcing gaseous uranium hexafluoride through semi-permeable membranes. This produces a slight separation between the molecules containing 235 U and 238 U. Throughout the Cold War, gaseous diffusion played a major role as a uranium enrichment technique, and as of 2008 accounted for about 33% of enriched uranium production, but in 2011 was deemed an obsolete technology that is steadily being replaced by the later generations of technology as the diffusion plants reach their ends of life. In 2013, the Paducah facility in the U.S. ceased operating. It was the last commercial 235 U gaseous diffusion plant in the world. Thermal diffusion. Thermal diffusion utilizes the transfer of heat across a thin liquid or gas to accomplish isotope separation. The process exploits the fact that the lighter 235 U gas molecules will diffuse toward a hot surface, and the heavier 238 U gas molecules will diffuse toward a cold surface. The S-50 plant at Oak Ridge, Tennessee was used during World War II to prepare feed material for the AMS process. It was abandoned in favor of gaseous diffusion. Centrifuge techniques. Gas centrifuge. The gas centrifuge process uses a large number of rotating cylinders in series and parallel formations. Each cylinder's rotation creates a strong centripetal force so that the heavier gas molecules containing 238 U move tangentially toward the outside of the cylinder, and the lighter gas molecules rich in 235 U collect closer to the center. It requires much less energy to achieve the same separation than the older gaseous diffusion process, which it has largely replaced, and so is the current method of choice and is termed second generation. It has a separation factor per stage of 1.3 relative to gaseous diffusion of 1.005, which translates to about 1/50th of the energy requirements. Gas centrifuge techniques produce about 54% of the world's enriched uranium. Tzipi Centrifuge. The Tzipi Centrifuge is an improvement on the standard gas centrifuge, the primary difference being the use of heat. The bottom of the rotating cylinder is heated, producing convection currents that move the 235 U up the cylinder, where it can be collected by scoops. This improved centrifuge design is used commercially by Renso to produce nuclear fuel and was used by Pakistan in the nuclear weapons program. Laser techniques. Laser processes promise lower energy inputs, lower capital costs and lower tails assays, hence significant economic advantages. Several laser processes have been investigated or are under development. Separation of isotopes by laser excitation is well advanced and licensed for commercial operation in 2012. Atomic vapor laser isotope separation. Atomic vapor laser isotope separation employs specially tuned lasers to separate isotopes of uranium using selective ionization of hyperfine transitions. The technique uses lasers which are tuned to frequencies that ionize 235 U atoms and no others. The positively charged 235 U ions are then attracted to a negatively charged plate and collected. Molecular laser isotope separation. Molecular laser isotope separation uses an infrared laser directed at UF6, exciting molecules that contain a 235 U atom. A second laser frees a fluorine atom, leaving uranium pentafluoride, which then precipitates out of the gas. Separation of isotopes by laser excitation. Separation of isotopes by laser excitation is an Australian development that also uses UF6. After a protracted development process involving U.S. Enrichment Company USEC acquiring and then relinquishing commercialization rights to the technology, GE Hitachi Nuclear Energy signed a commercialization agreement with Silex Systems in 2006. GE has since built a demonstration test loop and announced plans to build an initial commercial facility. Details of the process are classified and restricted by intergovernmental agreements between United States, Australia, and the commercial entities. Silex has been projected to be an order of magnitude more efficient than existing production techniques, but again, the exact figure is classified. In August 2011, Global Laser Enrichment, a subsidiary of GE, applied to the U.S. Nuclear Regulatory Commission for a permit to build a commercial plant. In September 2012, the NRC issued a license for GE to build and operate a commercial Silex enrichment plant. Although the company had not yet decided whether the project would be profitable enough to begin construction, and despite concerns that the technology could contribute to nuclear proliferation. Other techniques. Aerodynamic processes. Aerodynamic enrichment processes include the Becker jet nozzle techniques developed by E.W. Becker and Associates using the Liga process and the vortex tube separation process. These aerodynamic separation processes depend upon diffusion driven by pressure gradients, as does the gas centrifuge. They in general have the disadvantage of requiring complex systems of cascading of individual separating elements to minimize energy consumption. In effect, aerodynamic processes can be considered as non-rotating centrifuges. Enhancement of the centrifugal forces is achieved by dilution of UF6 with hydrogen or helium as a carrier gas, achieving a much higher flow velocity for the gas than could be obtained using pure uranium hexafluoride. The Uranium Enrichment Corporation of South Africa developed and deployed the continuous Helix and vortex separation cascade for high production rate, low enrichment, and the substantially different semi-batch Pelsicon low production rate high enrichment cascade, both using a particular vortex tube separator design, and both embodied an industrial plant. A demonstration plant was built in Brazil by Nuclei, a consortium led by Industrias Nucleares de Brazil that used the separation nozzle process. However, all methods have high energy consumption and substantial requirements for removal of waste heat. None are currently still in use. Electromagnetic isotope separation. In the electromagnetic isotope separation process, metallic uranium is first vaporized, and then ionized to positively charged ions. The cations are then accelerated and subsequently deflected by magnetic fields onto the respective collection targets. A production-scale mass spectrometer named the Calutron was developed during World War II that provided some of the 235 U used for the Little Boy nuclear bomb, which was dropped over Hiroshima in 1945. properly, the term calutron applies to a multi-stage device arranged in a large oval around a powerful electromagnet. Electromagnetic isotope separation has been largely abandoned in favor of more effective methods. Chemical methods. One chemical process has been demonstrated to pilot plant stage but not used. The French CHEMEX process exploited a very slight difference in the two isotopes' propensity to change valency in oxidation reduction, utilizing immiscible aqueous and organic phases. An ion exchange process was developed by the Asahi Chemical Company in Japan, which applies similar chemistry but affects separation on a proprietary resin-ion exchange column. Plasma separation. Plasma separation process describes a technique that makes use of superconducting magnets and plasma physics. In this process, the principle of ion cyclotron resonance is used to selectively energize the 235U isotope in a plasma containing a mix of ions. The French developed their own version of PSP, which they called RCI. Funding for RCI was drastically reduced in 1986, and the program was suspended around 1990, although RCI is still used for stable isotope separation. Separative work unit. Separative work. The amount of separation done by an enrichment process is a function of the concentrations of the feedstock, the enriched output, and the depleted tailings, and is expressed in units which are so calculated as to be proportional to the total input and to the mass processed. Separative work is not energy. The same amount of separative work will require different amounts of energy depending on the efficiency of the separation technology. Separative work is measured in separative work units SWU, kilogram SW, or kilogram UTA. 1 SWU equals 1 kilogram SW equals 1 kilogram UTA. 1 kSWU equals 1 TSW equals 1 T UTA. 1 MSWU equals 1 KTSW equals 1 not UTA. Cost issues. In addition to the separative work units provided by an enrichment facility, the other important parameter to be considered is the mass of natural uranium that is needed to yield a desired mass of enriched uranium. As with the number of SWUs, the amount of feed material required will also depend on the level of enrichment desired and upon the amount of 235U that ends up in the depleted uranium. However, unlike the number of SWUs required during enrichment, which increases with decreasing levels of 235U in the depleted stream, the amount of new needed will decrease with decreasing levels of 235U that end up in the DU. For example, in the enrichment of LeU for use in a light water reactor, it is typical for the enriched stream to contain 3.6% 235U, while the depleted stream contains 0.2% to 0.3% 235U. In order to produce 1 kilogram of this LeU, it would require approximately 8 kilograms of Nu and 4.5 SWU if the DU stream was allowed to have 0.3% 235U. On the other hand, if the depleted stream had only 0.2% 235U, then it would require just 6.7 kilograms of Nu, but nearly 5.7 SWU of enrichment, because the amount of Nu required and the number of SWUs required during enrichment change in opposite directions. If Nu is cheap and enrichment services are more expensive, then the operators will typically choose to allow more 235U to be left in the DU stream, whereas if Nu is more expensive and enrichment is less so, then they would choose the opposite. Uranium enrichment calculator designed by the WISE Uranium Project. Downblending. The opposite of enriching is downblending. Surplus HAU can be downblended to LAU to make it suitable for use in commercial nuclear fuel. The HAU feedstock can contain unwanted uranium isotopes. 234U is a minor isotope contained in natural uranium. During the enrichment process, its concentration increases but remains well below 1%. High concentrations of 236U are a byproduct from irradiation in a reactor and may be contained in the HAU, depending on its manufacturing history. HAU reprocessed from nuclear weapons material production reactors may contain 236U concentrations as high as 25%, resulting in concentrations of approximately 1.5% in the blended LAU product. 236U is a neutron poison. Therefore, the actual 235U concentration in the LAU product must be raised accordingly to compensate for the presence of 236U. The blend stock can be new or DU, however, depending on feedstock quality. SEU at typically 1.5 WT%. 235U may be used as a blend stock to dilute the unwanted byproducts that may be contained in the HAU feed. Concentrations of these isotopes in the LAU product in some cases could exceed ASTM specifications for nuclear fuel, if new or DU were used. So, the HAU downblending generally cannot contribute to the waste management problem posed by the existing large stockpiles of depleted uranium. A major downblending undertaking called the Megatons to Megawatts program converts ex-Soviet weapons-grade HAU to fuel for U.S. commercial power reactors. From 1995 through mid-2005, 250 tons of high-enriched uranium was recycled into low-enriched uranium. The goal is to recycle 500 tons by 2013. The decommissioning program of Russian nuclear warheads accounted for about 13% of total world requirement for enriched uranium leading up to 2008. The United States Enrichment Corporation has been involved in the disposition of a portion of the 174.3 tons of highly enriched uranium that the U.S. government declared as surplus military material in 1996. Through the U.S. HAU downblending program, this HAU material, taken primarily from dismantled U.S. nuclear warheads, was recycled into low-enriched uranium fuel, used by nuclear power plants to generate electricity. A uranium downblending calculator designed by the WISE Uranium Project. Global enrichment facilities. The following countries are known to operate enrichment facilities: Argentina, Brazil, China, France, Germany, India, Iran, Japan, the Netherlands, North Korea, Pakistan, Russia, the United Kingdom, and the United States. Belgium, Iran, Italy, and Spain hold an investment interest in the French Eurodif enrichment plant, with Iran's holding entitling it to 10% of the enriched uranium output. Countries that had enrichment programs in the past include Libya and South Africa, although Libya's facility was never operational. Australia has developed a laser enrichment process known as SILEX, which it intends to pursue through financial investment in a U.S. commercial venture by General Electric. It has also been claimed that Israel has a uranium enrichment program housed at the Negev Nuclear Research Center site near Diamona.